some of the elements in the periodic table have similar chemical and physical properties. So initially the periodic table was arranged based on those similarities in chemical and physical properties. That was done by Dmitry Mendeleev. But now we know that the periodic table is arranged based on electronic structure of the elements.
Let's go. This is more. Every child that wants to make it one day. Zimbo say class and presence of mind is elsewhere. Bring out Uzuzani, I've not moved exactly. Already Alispani and the timer is nowhere. I know your pain, you don't have to be scared. The dreams are very pure, lay the reason and focus. Keep that pen and paper, they will take you to that day. In the meantime, stand up, help.
What's up, everybody? Welcome back to Basic Chem 101 with Sihlebonani. My name is Sihlebonani, and please don't forget to subscribe. Don't forget to share this video. And today we are focusing on the electronic structure, or we are starting with our focus on the electronic structure of atoms. And if you looked at our previous video, we were talking about quantum numbers, and we said each atom or each electron in an atom has 4 quantum numbers, which is your principal, your angular momentum, your magnetic, and spin quantum numbers. So the first 3, we said they focus on the orbitals of the atom, and the 4th one, or the last one, it focuses on the spin orientation of the electron. So this is the spin quantum number, which is ms. This is where we'll focus for our lesson for today, the spin quantum number. Now, the discovery of the spin quantum number was found when hydrogen gas or hydrogen gas electrons were put in a magnetic field. So a beam of hydrogen gas atoms was put in a magnetic field. So this beam of hydrogen electrons, hydrogen gas has only 2 electrons. So what was expected is that these electrons would either go to one direction, which is they either go up or they either go down. But every time one electron would go this side, and then one electron would go this side, and then this one would be your positive, a half spin quantum number, and then this one would be your negative, a half spin quantum number. So this is how they discovered the magnetic spin of electrons. They say that these electrons also create a magnetic field of their own. But we will not get much into that. What we want to get into is, since now that we know where our electrons are most likely to be found in an atom, we would want to know the distribution of those electrons in a particular atom or in a particular element. Now, the distribution of those electrons in an element is called your electron configuration. So electron configuration is the distribution of electrons into available orbitals. So we know that we have shells in an atom, which is your K shell, your L shell, your M, and your N. And your principal quantum number here would be 1, 2, and 3, and so on. So you want to know the distribution of electrons. If you have these shells, you have subshells inside the shells, and in your subshells are distinguished by your angular momentum quantum number. So if you have your angular quantum momentum, which is L. And then when L is equal to 0, you have a subshell which is S. Then when it is 1, you have a subshell which is P. And then you have D. So you want to know how these electrons in your element are distributed in the shell and also in your subshell. Is it your S, your P, or your D orbital? So let's say your element is lithium, and lithium has 3 electrons. Now, if you're talking of an electron configuration of lithium, in lithium, if you have 3 electrons, it means you'll have, when N is equal to 1, you have 1s, which is the first shell, and then in the first shell, you only have the s orbital, because when N is equal to 1, you only have L, which is equal to 0, right? So in the subshell S, you can only have 2 electrons, and then you have 2. In the second shell, you have your S and your P orbital, but now you have 3 electrons. So in the second shell, you will have 1 here if you have 3 electrons for lithium. Let's say now you have neon. Neon has 8 electrons. The electron configuration would be 2s, 2, your 1s, 2, because in the first, or in the principal quantum number, you have L is equal to 0, and you can only have 2. Then you have 2 S2, then you have 2 P6. Then you have 8 electrons. That is your electron configuration. But now these subshells, your S, your P, or your D subshells, they also have their own suborbitals. Now you would want to know how these electrons would be distributed in those suborbitals of a particular atom. And then for that, you will be talking about orbital diagrams. Now let's erase some of this. If you look at orbital diagrams, these orbitals, you would draw them as circles. So if I have 3 electrons, it means for my 1s, I have 1 circle, and then I have 2s, then I have 2p. Now if I have 3 electrons, it means here I'll have 2 electrons, then I'll have 1 electron, then that is 3 electrons. Now the orbital diagrams, these are the ones that talk a lot about that illustrate a lot the spin quantum number. Now, to help us in the distribution of electrons in orbitals, there is a principle called the Polis exclusion principle, which says that no 2 electrons in an atom can have the same set of quantum numbers. So that is your Pauli exclusion principle. Now what does this mean? So here you have 1s, so quantum number n here is 1, and then your quantum number L will be 0, because it starts from 0 to n minus 1. And then your quantum number ML will be 0 as well, because it depends on L. And then your quantum number MS would be plus half or minus a half. So this Pauli's exclusion principle helps us in putting that in place. So if it means if this one is plus half, this one electron in one s, the next one has to be looking at a different direction. So the first three quantum numbers for this shell are the same, but the last one, which is the spin quantum number, is not the same. So the whole set is, or these two electrons do not have the same set of quantum numbers. So you can differentiate between the two if you are talking about the one that is pointing up or the one that is pointing down based on the spin. So the spin can only be a plus half and also minus a half. So that means an orbital, which is these circles in this case, can only accommodate 2 electrons. So if this one is filled, you will have to move to the next one. Now, if we are talking about 3 electrons, it would end here. So this one has its own quantum numbers different from this one. But if we had 8 electrons, I would have 2 here, 2 here, and 2 here, but the different spins. So now let's look at some examples based on only the Pauli's exclusion principle, because that is what we have only talked about for now. Let's look at if some of these examples are possible or not possible based on Pauli's exclusion and the spin quantum number. So if you have 1s, you have 2 electrons, and you have 2s, you have 1 electron. This one, according to Pauli's exclusion principle, here the spins are not the same. Here you have 1 electron. So this one is correct. But if you look at this one is right, but here you have 3. And we said because we can only have 2 spins in an orbital, which is half and minus a half, an orbital can only accommodate 2 electrons. So here you have 3. If you have 3, it means this one and this one, which is this and this, have the same set of quantum numbers. So the Pauli's exclusion principles, it doesn't apply here. So for this one is not possible. It would be possible if one of these would maybe have moved to the p orbital. Then if we look at this one, based on Pauli's exclusion principle, this one has the same set, or these two have the same set of quantum numbers because they are pointing in the same direction. So this one is not correct. Then if we look at this one, based on electron configuration, 1s2, 2s1, 2p7. So this one is not correct because p can accommodate up to 6 electrons. So this one is not correct. Now, because of this, as we wrap up, how do you know that each subshell, your s, your p, your d orbital, how many electrons can it accommodate? Now, each orbital like this can accommodate only 2 electrons. But how do you know how many suborbitals are there? The formula to know it is it's 2 times L plus 1. For an example, if L is equal to 0, so it's 0 plus 1. You have 1 orbital, which is in the s shell, you have 1 orbital. In the s shell, you have 1 orbital. And then if you are in the p shell, which is, it's 2 times 1 plus 1. So it's 2. It means you have 3 orbitals. So in the p shell, you have 1, 2, 3. So you have 3 orbitals in the p shell. Then in the d orbital, it's 2 times 2 plus 1. So you have 5. You have 5 orbitals in the d orbital. And then in the f orbital, you have 2 times 3 plus 1, which is equal to 7. Now you know that each orbital in a subshell can accommodate only 2 electrons. So if I am in the s orbital, it's 1 orbital, so I can have 2 electrons. Then if I am in the p orbital, which is 1, can have 3 orbitals, and then it means I can have a maximum of 6 electrons. And then for the d orbital, I can have a maximum of 10 electrons. Then for the f orbital, I can have a maximum of 14 electrons. So that is how you know how much electrons you can put in a suborbital. And for today, we can stop there, and that is the explanation of the Polis exclusion principle and the application of the spin quantum number. I hope you have learned a thing or two from today's session, and I hope you like the video. I also hope that you will share it. Please don't forget to subscribe if you haven't already, because your support is helping us to do more with these videos. Thank you very much for watching. This has been Basic Chem 101 with Sihlebonan. My name is Sihlebonan. This is the Helton Nation.